All right, good morning chemistry. Today we're going to be working on specific heat and heat capacity, calorimetry, and the transfer of heat between objects. So, to begin, we have a reaction, and the reaction is going to be between hydrochloric acid, so HCl, and sodium oxide. All right, so both of these are going to be aqueous. All right, so we'll do that in parentheses. They're both aqueous solutions. And now, what are these going to produce? Now, I'm going to have to write that down here, but these produce sodium chloride, salt, and AQ, and water, H2O. All right, and that's going to be a liquid. Okay, so we have sodium chloride, NaCl, or NaOH, and those are going to produce water. So now let's take a look at the different amounts that we're working with. Okay, so we have 50 milliliters of 1 molar HCl, so we'll do that up there. 50 milliliters of 1 molar HCl, right? And that's going to be at a temperature of 22 degrees Celsius, right? And then we also have 50 milliliters of 1 molar sodium oxide, 1 molar NaOH at 22 degrees Celsius as well. All right, so the problem is that these two things are going to get mixed together, and they're going to have a final temperature, a maximum temperature of 28.9 degrees Celsius. So basically 29 degrees Celsius. All right, 29 degrees Celsius is going to be our T max. Okay, so we got our T max, we have our initial volumes and temperatures, and we have this reaction. Now, there's a certain rule or a certain process with these types of problems, and there's a fundamental assumption. All right, and so that fundamental assumption is that the heat produced from the reaction, or the change in heat from the reaction, you'll know that heat is represented by the variable Q. So the heat of the reaction is going to be equal and opposite to the heat of the solution. All right, so what this means is any energy change between these two is going to be equal and opposite because energy is conserved, all right? So if the energy in the reaction increases by 36 joules, that means the energy in the solution decreases by 36 joules. It's going to be the same. And that's going to allow us to discover a lot of different properties about this reaction, about the reactants in the solution, just based on this one law or observation that energy is going to be conserved. So the formula we're going to work with is that Q is equal to the specific heat times the mass times the change in temperature. Right? Specific heat times the mass times the change in temperature. All right? You also might see this written as MCAT because that's a little bit easier to remember. So because these are all multiplication, we can reorder them however we want and we'll still get the same answer. So some people write mass, specific heat, delta T, or change in temperature, because then you get MCAT and it's a little bit easier to remember. All right, so we have MCAT. Now, how do we get to what we're looking for, which is the amount of heat produced by this reaction? So we want to find Q reaction. All right, and so to do that, we're going to take the specific heat of the solution, we're going to take the mass of the solution, and we are going to take the change in temperature. Now, the change in temperature, so the heat of the reaction is going to be opposite of the change in temperature, or change in heat from the solution. All right, so we're going to have a negative of whatever this is. Specific heat, well, here we have to rely on a few assumptions. So you'll notice that both of these are aqueous, and the product is also aqueous and a liquid. So for the conversion from volume to grams, we can actually use the density of water. So again, if you look at our givens, we're not given a mass, we're only given a volume. So what we gotta do is convert these milliliters to grams. All right, so in order to convert milliliters to grams, we need a conversion factor, and that's going to be the conversion factor for water, which is 1 gram is equal to 1 milliliter. All right, so if 1 gram is equal to 1 milliliter, and we have 100 milliliters total solution, we would have 100 grams. So I'm going to erase this quickly. And for our first, for our mass, we have 100 grams. Now, what about the specific heat? Well, since this solution is mostly water, we can use the specific heat for water, which is 4.184, and then the units are going to be joules per grams degrees Celsius. All right, so there we have the specific heat. Again, we can use water because these are all dissolved in water anyway, and that's going to be the majority of the solution. All right, then last thing we need is the change in temperature. For that, we're going to take our T final, or our final temperature, minus our initial. So that's going to be 29 minus 22 degrees Celsius. And we're going to put that in parentheses so we know to do that first. All right, so adding these all together, this is going to come out to 7 degrees Celsius. This is going to come out to 100 grams. And this is going to stay the same as 4.184 joules per grams times degrees Celsius. And we should get a grand total of Q is equal to 2,900 joules. Right, because the grams cancel, the Celsius, degrees Celsius cancels, so we get 2,900 joules. Now, because Q reaction is going to be negative Q solution, this is actually going to be a negative number. So we could have added that in at any point in our equation. We just need to make sure we add in the negative at some point because it is opposite here. And so for our answer, we have Q is equal to negative 2,900 joules. And that is the change in temperature, or the amount of energy released from this reaction between hydrochloric acid and sodium oxide. So for your homework, you have 2 conceptual questions, numbers 14 and 15. Go ahead and answer those. Let me know if you need anything, and I will see you in the next video. Let's finish these next 3 weeks strong.